Welcome everybody to the February meeting of the Mornington Peninsula Astronomical Society, and I've peppered it with green throughout for some reason. What I'll do is I'll start off with the first screen, and then we'll go through. Chris is not here tonight, so he has sent through slides for Astro Mo Pho, and I'll try and talk to those as best I can. Starting off up here, the University of Melbourne has just recently received $90 million for a ARC Centre of Excellence into plants for space. So in other words, as part of the Artemis mission to Mars, they're looking at clever things to do with plants in space in terms of not only propagation, efficiency, but other things that they can be used for, medicines and food. And that's in collaboration with 3 other universities in different states, and that should prove very interesting over the next 7 years, which they've been funded for. Next one down here, the little box of tricks up there, 5 of those were launched, didn't really make it onto the news. They're Australian satellites. They're each about 300 kilograms, so they're not tiny little things by any means. And 5 of them were launched from Cape Canaveral a couple of weeks ago. And they're successfully up in orbit, and they're air traffic control management being used. So they are Australian designed and built, just launched overseas, and they're the first 5 of 200. So we're going to be putting up an awful lot for air traffic control management over Australian skies, but none of that sort of made it into the news at all, given that it's the biggest and most complicated satellite Australia's ever put together. Over here is, you may, if you're on Facebook, have seen that post that Greg Walton made. He's not here tonight. And I'd have to say it looks very green to me over here. So this is a 1-hour time exposure that he took up at Heathcote, which is north of Melbourne, so you don't have the lights of Frankston and Melbourne in the way. You're just mainly contending with more distant towns like Bendigo. Shown on the left there is the planet Mars. Those who were here on the 10th of February for the Comet night would have seen a similar configuration to this. This was taken the night after, but you can see the motion of the period of 1 hour of the comet relative to Mars. So you can see it's definitely a solar system orbiting object. So that was taken with a 6-inch refractor, which I think is about the same size as Big Blue down the observatory, around that particular size. And down the bottom, there's been lots of UFOs and IFOs in the media lately. And I have noticed Nina's 99 Luft balloons, red balloons, have been playing on the radio quite a bit lately. And the connotations there, of course, are the balloons that are being shot down over the US and Canada. And I believe one even went over Central America as well, sorry, South America as well. And so not all of those have been confirmed as balloons. They may indeed have shot down weather balloons or drones or something else, but they're keeping fairly tight-lipped so far on the next 3 that got shot down. So tonight, as usual, we'll look through the past events of the previous month and the up-and-coming month. Then I'll actually swap the order to minimise the change of connections here, because we'll be having a few issues. So I'll then do Chris's MoPho challenge through his slides that he's prepared, then hand over to Mark for Sky for the month. Then we'll look at the main talk, or rather there will be 2 talks by the same lecturer. It will be Dr. Cameron Hummels of California Institute of Technology. It was California Institute of Technology that first discovered the comet, ZTF, the Green Comet. And this particular talk was given only about a week ago, so it's fairly recent. And then an older talk that he gave during his postdoc years, I think, on simulating the universe on a supercomputer. So he's a computational astrophysicist at California Institute of Technology. Then we'll look at a video that goes for about 10-15 minutes on the tour of the factory that actually produced the Artemis rocket that went to the moon, and Artemis 1 came round and back, and you'll see how it's made, and you'll see the size of things. And then we'll close right at the end with a bit of Gangnam Style for something different from NASA. So, recent events. We had the working bee at the Briars on the 21st of January, and all went well with that. I do notice the paths out there have been pressure cleaned, because you can see all the little black spots on them, so we know Phil's been very busy. On 25th of January we had the committee meeting where we finalised the design of the marquee. The Society is ordering in, or in fact has ordered in, a large 6x3 marquee with our logo, and it'll be a mean black colour, so it should look rather interesting standing out, and hopefully we get it in time for the Somerville Family Fun Day. Chris reported back on the survey, and he may say something on that at next month's meeting, and also looked at the flyer updates for the Society. These are the ones that get handed out to various visitor centres and any public inquiries that go on. And he and his wife Nikki, Chris and his wife Nikki, have done an excellent job of having that put together as probably about a version 5 of that flyer over the years, and it looks pretty swish. The last public night in January was given by Guido, who's quickly about to walk out the room probably. 0% cloud, and a good number of public there on the night. So in other words, they all turned up and more, probably because of the low level of cloud. 3rd of February, which is the regular February public viewing night, Manfred Berger had sort of mixed weather conditions. It was pelting with hail in Dramana, I believe, and we were fortunate enough here to be able to break the talk into half and get people outside to look at the sky during a gap in the clouds before the weather closed in again here. So things were a lot better here at the Briars. February 10th we saw the Green Comet here at the Briars. I must admit, when I looked through the telescopes that were set up, I couldn't detect any green unless I actually put these laser goggles on. These are actually 532 nanometer infrared laser goggles, which you can buy. They're also very handy if you know anyone with migraine, because migraine is actually least sensitive at that particular wavelength by good coincidence. And in fact, that was the original reason for buying these. Then 14th of February, we didn't do a specific Valentine's Day event, but Guido kindly asked ChatGPT, the online artificial intelligence service, to concoct us a poem for Valentine's Day to do with the Green Comet. And the artificial intelligence, within a matter of nanoseconds, came up with what's shown down there as its poem for Valentine's Day. So hopefully you've all read that now and go, ah. On to the next one. Coming up soon, Working Bee this weekend. I imagine there's still things to be done. No planned committee meeting next week, given that we've got a couple of people away, unless committee particularly wants anything. There's nothing urgent and pressing. Most of that was covered last committee meeting. So a few people are absent at the moment. 25th of February, Telescope Learning Day here at the Briars. We're pretty nearly fully booked, so 49 booked at the moment. So I think officially there's only one more seat to go, although I'm sure we could probably squeeze a couple more in if there was a couple from a family if needed. 3rd of March, Public Stargazing Night. Trevor's going to be talking at that one. We've already got 86 booked for that, so that one is well and truly full. 4th of March, which is the Saturday afterwards, we've got the musical trivia night here at the Briars in conjunction with the Southern Peninsula Concert Band. They were the band that actually played in this room here back in 2019 with the Apollo concert that we put together with them. We've so far got about 50 odd booked for that, and so if you're interested in that, do so online while there are still seats available. This one will be outdoors rather than indoors, obviously because of COVID and that, whereas last time the band was actually at the front here, just about level with the front seats here, and we managed to cram, oh gosh, about 80 to 100 people in the rest of the room, which we'd be a bit reluctant to do these days. About a week and a bit later, on the 13th of March, which is the Monday of the Labor Day weekend, so it's a public holiday on that day. That's the Somerville Family Fun Day at the Fruit Growers Reserve, which is near the Funny Double Roundabout in Somerville on the western western side of the railway line. So it should be relatively easy to find. Just look for a gathering of 10,000 people, which is how many they're expecting this year. So that's probably a good 50% more than we saw even at Bentley, and there was an awful lot of people at the Bentley Festival, so we're expecting more. And we've also been given pride of place in the positioning right in the centre of their football oval facing north, so we'll have a good vista and a good position and right centre stage. 15th of March is the next meeting here. Next cosmology interest group is not going to be until later in March, on Saturday the 25th of March. And for those couple of dozen members who booked tickets to the brown and green talk up in Melbourne at the Melbourne Convention Centre, that's also fast approaching on the 3rd of April. So I'll skip Sky for the month for the moment. We'll come back to Mark. And we'll look at Chris's Mo Pho for the month. Hopefully I don't mess it up too badly. Right, so last month's target challenge for those who wanted to try taking pictures of the night sky, either through sophisticated or modest equipment, was anything to do with the Orion constellation was the challenge. And those who actually submitted something are shown on the left-hand side there. We've got Nerida Landcake, Nick Axeris, Guido Tack, Ben Claringbold, Chris Black, Chris Kostakanellis, and Dominic Lucarelli. And now we'll look at some of what was submitted. So here's Guido's one, and can you tell what that is by the shape of it? So as Guido kindly says here, it's called the Monkey Head Nebula. Can you see why it's called a monkey head? Pretty clear, isn't it? There's like the face there and a couple of eyes and the nose, and there's the back of the head of the monkey there. So once you've seen it and it's in the right orientation, it's hard not to see it. So really nice image, that one. Then we've got Ben Claringbold, who's not here tonight, took one of the Orion Nebula itself, using his William Optics one. So he took several it's like 5-minute exposures, 12 of them, and added them all together to bring out extra detail. Anders Hamilton, who he's sitting at the back, took, was this one naturally taken from Mount Martha yourself? Yep. And this one's also of the Orion Nebula there, and I'm not sure if it turns out too well here, but you can see some detail down there of the horse head, I think, as well. And Chris Black with a much blacker background there, and taken from Melbourne, so I'm not sure where in Melbourne he was able to actually take that photo, but very black background. And you can sort of see the Horsehead Nebula in there as well, over there. And Chris, who's in New Zealand at the moment, took this of M78 and Barnard's Loop, and I'm not sure whether you can make out the loop spreading across the screen under the light level, or it might just be my green glasses is cutting it off, which I suspect it is. Then Dominic Lucarelli had Orion's Belt, which is those 3 stars there, and obviously the Orion Nebula itself. That was just taken on with a Canon camera and a long lens, 105mm lens, and a tracking mount, so no telescope involved with that one by the looks of it. And Nerida took out her trusty phone and took this snapshot of the Orion Nebula there. There's a sword of the Orion there, and the belt stars, and the head and the arm and the 2 legs of Orion the Hunter. And again, where was that one taken, Nerida? Oh, that was taken up at Heathcote as well. And Nick Axeris comes in with a heck of a lot of detail in his. He says location Melbourne, but I'm not sure how far out of Melbourne he actually was, but using a particular filter there and very, very long exposures added together for that one, but shows lots and lots of colour and lots of detail. So what's the next month's target? Well, Chris has set it for southern open clusters, and he emphasises it's not the globular clusters, so no good having Omega Centauri or 47 Tucani. It has to be the open clusters. They're the ones which are fairly sparse in the sky, such as the jewel box near the Southern Cross and these other ones that are here, and I'm sure there are plenty others to go for as well. I'm just waiting for Chris to pick something easy like the moon or something like that to have a go at. Oh yeah, they are amazing. Yeah, they're amazing what the members have taken. Yeah, absolutely so. And a lot of hours would have gone into those as well. A lot of hours. So if you wish to submit something, even if it's, as you saw, just from your phone or a digital camera and that, perfectly fine, give it a go. And as Chris says here, just either submit them to, if you're on Facebook, to the MPAS members Facebook page, or email them to eScorpius, which is the email group. And he said put in the subject matter Astro Mo Pho, so he knows it's one of the ones you're sending in, or you can just email it straight to Chris there at his email address. And if you forget those details, you can just look up tonight's recording online and see any details of these slides very easily. And with that, I'll throw over to Mark.
Righto, now that I've finally got the technology working, on with Sky for the month for February. Can't help but feel the year is disappearing quick. During February, March, the new moon is on the 20th of the 2nd, so in a few nights' time, for those who want to get their cameras out and get some dark sky stuff. And the full moon will be due on the 7th of March. Things to look for, on the 15th of the 2nd, which is tonight. Unfortunately, there's a bit of cloud there at the moment. Neptune is 0.2 degrees northeast of Venus. Now, if you hold your thumb up at arm's length, that's 0.5 of a degree. So it's 2/5 of the width of your thumb. So fairly close. The only problem is, have I dropped out? The only problem is Venus is still in the twilight zone of the sun, and while Venus is big and ugly enough to shine through that, I'm not sure you'll actually be able to pick up Neptune, purely because of the distance and how faint it is. Comet ZTF, the one we've all been looking at, is 1.7 degrees, so about 3 thumb widths southeast of Aldebaran, which probably gives everyone a bit of a chance to find it, because Aldebaran's reasonably easy to find. At the moment you've got Mars and then you've got Aldebaran. So Aldebaran's the not so bright red one, and ZTF is just southeast of that. Comet Wild is another one. It's northeast of Chi-Ophiuchi, which basically means it's a morning object after midnight. On the 17th, Saturn will be in conjunction with the Sun, so we won't be able to see Saturn probably until the end of next month. And you'll have to get up in the morning if you want to see it then. Moon at perigee, closest approach to Earth on the 19th, but if you notice there, it'll be a new moon, so it's got to be a big new moon. Really worth looking at, won't it? Okay, Comet Pan-STARRS, about 3 degrees southeast of Achernar. Achenar's another one fairly easy to see, and we'll have a look at the sky in a second and I'll show you where Achernar is. Jupiter's about 0.5 degree south of Venus on the 2nd of the 3rd at 7 p.m. It'll be getting a little bit darker then, days will be getting shorter, and given that Jupiter's fairly bright and Venus is fairly bright, you should be able to see both of them, and what are they, about 6 thumb widths apart, so not all that far. And ZTF is 0.1 degrees, so 1/50 thumb width. west of NGC 1637, and the reason I put that there is a lot of people have go-to scopes. If you type in the NGC and you go to that object, you should be able to see the Comet ZTF. Just depends, it's starting to fade a little bit at the moment. I expect by the end of February it'll be about 9th magnitude. And the Gamma Normids meteor shower starting on about the 25th of the 2nd to the 28th of the 3rd. I'll have a little bit more about them later on. So looking at the sky, looking to the south, we've got a couple of things worth having a look at the moment. We've got obviously the two globular clusters. They're the ones, don't photograph them for MoPho. They're globular clusters. We're looking at open clusters. So the open clusters on this chart, things like the Southern Pleiades, they're up here near the Eta Carina Nebula. Okay, that was one of the ones that Chris mentioned. Ghost of Jupiter is actually a planetary nebula. Looks very, very similar to Jupiter, but it looks like a ghost of Jupiter. In other words, it's kind of more ethereal rather than solid. And what it is, it's actually a star that compressed and then gave off its whole outer shell. So it's reasonably easy to find, and one worth targeting, particularly for the newer members. Looking to the north, we've got a couple more open clusters. These are here. So one in Gemini, easily found by the two bright stars, Castor and Pollux. You've also got one up here and one here, and these are all open clusters. So they're the ones to photograph for MoPho if you're looking for something to go for. And of course the Orion Nebula. It's always a good one for newbies to start off with. It's quite easy to find, and everyone knows where the saucepan is. So planets. Mercury has moved through its maximum elongation, so it's as high as it was ever going to get in the morning sky. It's not going to get any higher. It's now heading back towards the Sun, which will go into superior conjunction, and after that it'll pop out as an evening object again. It always depends on its relative position to the ecliptic plane as to whether it gets high in the eastern sky or whether it's fairly low, and I'm not terribly sure at the moment whether it's going to get high. Let you know in a couple of months. Venus is starting to rise further into the western sky. It's still in the glare of the sun, but it is easily spottable. If you look along the ecliptic, reasonable distance above the horizon now, you will actually see Venus quite clearly. Probably a good time to have a look at Venus too, because with the bright background, it's not so intense in your scope, and you're more likely to pick up a bit of detail than when it's got a black background. It tends to flare a bit in your scopes just because sheer brightness. Earth, well past the summer solstice, the days will be getting shorter, and I don't really think we had a summer, did we? The outer planets, Mars is now well past opposition. It's still well placed to view, but you've got to remember now it's getting a bit far away from us, so there's not a lot of detail to be seen with Mars. It's still an easy target, but really you're not going to see much more than a red dot in anything other than a reasonable size scope. Yeah, as it says there, it's in Taurus. It's just below Aldebaran. Aldebaran's a red star, so you've got two red objects in fairly close proximity. Jupiter is still visible in the western sky. In Pisces, it's still fairly good to view, and also like Venus, with a slightly lighter background, you can sometimes get a little bit more detail from it. You can still pick up its moons and that sort of stuff. So won't have it for much longer. It's not far off heading towards conjunction either. Saturn, as I said, left the evening sky, had its conjunction, or has its conjunction in 2 nights' time, and after a month or two, actually about the end of March, if you really have a desperate need to see Saturn, you're going to need to get up in the morning to see it. It'll be a morning object probably until about August, September, when it'll creep back into the evening sky. Uranus can be found in Aries. I think it's a little way between Jupiter and Mars at the moment. There's not a lot to look at with Uranus. It should show up as a bluish green disk in your telescope, and the main point of finding it is so you can say you've looked at Uranus through your own scope. And Neptune now is very low in the western sky, not very far from Venus, so it's probably starting to get into the twilight zone and may be rather difficult to pick up. And as said before, it has a very close pass with Venus. So the appearance of the planets at the moment, there's Mercury. It's at the moment it's heading back or heading around towards Superior Conjunction, which is why we're getting the large face, because it's going around the other side of the Sun. And so most of it's getting looked at. Venus, on the other hand, is coming towards us, travelling faster than Earth, so it will catch us up and pass it. But because it's an inner planet, we'll actually see it get high in the sky. It'll sit there for a little while and then it'll start descending again. As it comes towards us, though, it will turn more of its unlit back towards us. So what you'll see is very much a crescent like you do with the moon. And at the moment, it's still got probably just slightly forward of the Sun from where we are. So as it comes out and around, gets to its side-on view there, or maximum elongation, where you'll see about half, but it'll also get bigger as it gets nearer to us. Saturn, you'll notice over the last few months, if you've been watching this for the last couple of months, Saturn's actually got a lot smaller. You can't see it at the moment, it's the other side of the Sun, but it's as far away from us as it's going to get. Now, as it moves around, heads back towards opposition, it will actually increase in size. And as it comes back next year, the rings will actually close a little bit because in 2025, 2 years' time, we're going to pass through what's known as the ring plane, and you won't be able to see the rings of Saturn because they'll be edge on to us. Yeah. Jupiter, still very large. It's not all that far away, astronomically speaking, and obviously the largest planet in the solar system. So it's still a good object to track down with your scope and looking at your moon configurations. And a decent sized scope, you may still be able to pick up shadow transits. Uranus, as I said, it's still up in a reasonable position to have a look at, but there's not a lot to look at. Fair way away. If you do see any of its moons, you'll notice that they're vertical instead of horizontal. And the reason is it is rolling around there on its side. And Neptune, if you can see much more than a blue dot, you're doing all right, but it's not far off conjunction either, so probably won't see that again until the morning. Other stuff, still a few comets kicking around. Pan-STARRS K2 begins the month in Tucana, so not far from 47 Tucana. It moves into Hydrus on the 21st of the 2nd. It's around 8th magnitude, so you'll need a reasonable size scope to get it, but it's still probably achievable. And it is getting a little higher in the evening sky. The Tucana is up in that direction there. And as we go around, it's coming up. Pan-STARRS K1 is in Sagittarius, so it's a morning object. It's currently 12th magnitude, so it's one for the real diehards. Comet Wild 2 moved into Ophiuchus about 10th magnitude. It's rising in the southeastern sky around about midnight. Now, Ophiuchus is around about the tail, I think, of Scorpio from memory. So you'll need to wait till Scorpio comes up, which is early post-midnight. And Comet ZTF, as I said, is near to Aldebaran and the Hyades. If you're looking out there, you've got Aldebaran, and just to the right-hand side of it is the Hyades, to the left-hand side is the Pleiades. So it's in the vicinity of Aldebaran and the Hyades, and is setting around midnight. Yeah, we did have a look at it through the scopes here the other night, and it was not overly spectacular. It's not much more than a little smudge. And meteor showers, as I said, the Gamma Normids, getting active between the 25th of February and the 28th of next month, with a maximum around the 15th to the 3rd. And they don't have a high rate of meteors, with the maximum around the 15th getting to about 6 per hour. They do tend to be generally bright white, yellow and orange, and can sometimes leave a bit of a trail, so might be worth looking at. And if we go back, I'll show you, if I can find it. I did find it. Okay. Door prize to whoever can find Norman. Oop. All right, I apologise. I did have it, but can't find it now. Okay, so I'm sorry, you have to find that one for yourself. Okay, upcoming events, Saturday the 18th of February, starting at 4 p.m. is the members barbecue and working bee. So good opportunity to come along. There's usually someone here who can provide you with a bit of training on the observatory once, assuming the evening has got some reasonable sort of viewing and that sort of stuff. Certainly have a sausage and get to know people. And on the 25th of February, as Peter said, the Telescope Learning Day. Members don't need to book, and we've got, what, about 50 public, have we? So there'll be 2 talks. Where's Guido? You still happy to give the evening one? All right. So it'll be 2 talks on telescopes and the basics of telescopes and that sort of stuff. I'll be doing 1, maybe 2. Guido will be doing maybe 1. So I have to run away after the sausage. Okay. The information provided by Astronomy 2023, Wallace Dawson Northfield. There's still a couple left out there if anyone wants their own copy. And any questions? Damn it, I thought I was going to get away. Go ahead, Anne.
The Saturn and the rings, you say it's going to be at some point flat on.
Yep.
Does it go the other way as well?
Saturn's rings stay orientated towards the sun the same way. So as it goes around the sun, it goes around like that.
Yep.
So while it's there and the sun's there, the rings are opened up. But when it gets to a point where the sun's there and Saturn's there, the rings are kind of side on, and as we go between the sun and the rings, we won't see them. It happens every 7 years apparently. So as we pop out the other side, so the rings sort of appear to go like that.
But never fully sort of flat on.
They're never fully flat on. It's only tilted, I think, about 27 degrees. So the maximum open that you'll see them is 27 degrees, and the minimum is nothing. So 2025, got a couple of years yet. No worries. Any questions? Okay, thank you.
So tonight's speaker is Professor Cameron Hummels, astrophysicist from CalTech. So it was their little system that detected comet ZDF in the first place. So as I said, this talk about ZTF is about a week and a bit old. And the second talk by him, because both of these talks only go for about 25 minutes or so, and the second talk is on simulating the universe on a computer. So the first one about the comet. Looks very green, doesn't it?
Hello everyone, I'm Dr. Cameron Hummels, an astrophysicist at CalTech, and I'm going to talk about, for the next few minutes, the Green Comet and why it's so special, and putting it sort of in the context of what we know about it and comets in general. So the Green Comet has been in the news a large amount in the last few weeks as it comes into the inner solar system and gets bright enough to see with the naked eye. This presentation just gives some idea of how comets behave, what their origin is, what science they can allow us to do, and more about the discovery of the comet in general. So I'm referring to the Green Comet, but more specifically, this is comet C/2022 E3 ZTF, or as I'm just going to call for the rest of this presentation, Comet ZTF, kind of interchangeably. Now, the image of the comet is really spectacular. It is in fact green. I'll talk a little bit more about that in a few minutes. You can see a really nice tail. And I encourage you, if you have the opportunity to look through a telescope at it, you can see some pretty awesome views. But let's just start at the basics of putting this in context. What is our solar system? Everybody has some intuition for what our solar system is. This is a nice little cartoon showing many of the different objects in our solar system. And really, it consists of the planets and, of course, the sun at the center, moons, dwarf planets like Pluto and other friends of Pluto in the outer solar system, asteroids, comets, spacecraft, and dust and debris. And really, the extent of the solar system extends all the way out to almost a light year away from the sun. So what that basically means is the distance that light can travel in a year. And this is the equivalent to 60,000 astronomical units, which are the distance between the sun and the Earth. So if you think about how far away the sun is from the Earth, multiply that by 60,000, and that gives you the edge of the solar system. Now, why is that the edge? It's simply because that's kind of the region where the sun's gravity dominates over other forms of gravity. Once you go beyond around a light year away from the sun, other stars, other passing stars, or the gravitational potential from the galaxy itself kind of overwhelms things. And so you can think of, if I were to take a rock and drop it right on the interior of this circle, this outer edge, it would plummet in towards the center of the solar system and towards the sun. Whereas if I were to drop that same rock beyond the edge of this circle, it would probably not do that. It would either hang out around there or start traveling towards a different star or something else. So that's really why we call it the edge. And it's around this edge where comets appear to originate. So to answer our first question, what is our solar system? It's this region surrounding the sun, extending to around a light year away and containing all of the stuff that's orbiting around our sun. This is another sort of cartoon, basically diagramming what our solar system looks like. And of course, people are familiar with our planets, the inner planets, Mercury, Venus, Earth, and Mars, the asteroid belt, the outer planets, Jupiter, Saturn, Uranus, and Neptune, and then these other kind of mysterious objects in the outer solar system called the Kuiper belt and the Oort cloud. And this is more to scale of what our solar system looks like and the relative orbits of the objects in the inner solar system. And if we zoom out from this particular image, we see what the Kuiper belt is meant to be. So the Kuiper belt is kind of like a donut of objects in the outer solar system surrounding the planets in the inner solar system. That yellow circle represents the orbit of Pluto, which is a Kuiper belt. And again, this AU thing at the bottom designation is an astronomical unit, and that's the distance from the Earth to the sun. So like 30 times to 50 times that distance is where you find these objects in the Kuiper belt. And Kuiper belt is just named after a Dutch guy who proposed these things, named Kuiper. So you've got a bunch of icy objects in the outer solar system called the Kuiper belt, and then even beyond that, you can extend farther out to what's known as the Oort cloud, and that is this kind of spherical ball of different small objects in the outer parts of the solar system, going out to almost the edge of the solar system, where you find very icy objects that eventually sometimes fall into the inner solar system and become comets. And again, strangely enough, it's another Dutch guy that this is named after, Jan Oort. So as I said, these things are hanging out in the outer parts of the solar system, and because it's in the outer parts of the solar system, it's a long ways from the sun, and it's very cold there, and so these objects are composed of ices and dust and so on and so forth. And occasionally, one will undergo some sort of perturbation, maybe a passing star gets too close and it disrupts its orbit, and it causes it to start falling inward into the interior of the solar system. And when it does, it starts to heat up because it's getting closer to the sun, which of course is very hot. And it starts to showcase this characteristic shape of a comet with a tail and that sort of thing. And so really, where are the comets? Well, they originate in the outer parts of the solar system in this Kuiper belt and the Oort cloud, and sometimes they fall inward, and when they do, they heat up and start to outgas material from their surfaces that makes them have the traditional shape that we associate them with. So why do they look like this in the sky? Well, it's funny, the word comet comes from the Greek word kometes, which means long-haired. And it really does look like it has, a star with long hair here. But why is this the case? Why does it have this characteristic tail? We refer to these objects as dirty snowballs. This is a science demo I did a couple of years ago where we get to build a comet using dry ice and water and some other household materials. And dirty snowball really is a strong approximation for what these comets are. Because they form in the outer solar system where it's very cold, they're formed from a variety of different ices: dry ice, water ice, methane ice, ammonia ices, and mixed in with a bunch of dust and dirt and organic materials as well. So this is an actual image of a cometary nucleus, one of these dirty snowballs. This is comet Churyumov-Gerasimenko, which we actually had a European Space Agency lander called the Rosetta mission that landed and orbited around this for several years, about a decade ago. And this is an image, and it really does look like a dirty snowball. I mean, you can see it has some reflectance, but there's a lot of dirt and substructure on the surface. Now, these things are pretty small. Cometary nuclei like this are somewhere between, they can get as large as like 20 or 30 kilometers across, but for the most part, they're in the range of 1 to 10 kilometers, or 1 to 10 miles or something like that. Halley's Comet is about 10 kilometers or 6 miles across. The comet ZTF, the one that we're talking about today, is about 1 kilometer across, or about half a mile across. So it's really quite small. It's like the size of a small town, or even like a neighborhood. So really very small. And when it comes into the inner solar system, remember, it's starting to heat up and it's starting to melt and evaporate these ices. The technical term is sublimate, for when something goes straight from a solid like an ice into a vapor like a gas. And that's what's happening. And actually that mission, the Rosetta mission, which landed on comet Churyumov-Gerasimenko, took active video footage from the surface of the comet, which is really just mind-blowing and spectacular. This is from the surface of a comet taken about 10 years ago. And you can see, I mean, aside from the fact that this looks like a Game of Thrones scene on the wall, which is just crazy, you can see all kinds of snow and dust and debris that's being kicked off as this thing is starting to travel into the inner solar system and losing a lot of that material as it evaporates off the surface and gets kicked into orbit around it. So it's really spectacular. So as that ice and such is melting and evaporating from the surface, you form this gaseous cloud that surrounds that cometary nucleus. Remember, the nucleus is only like a kilometer or a mile in size. Well, this coma, it's called, the cloud that surrounds it of all of this gas, can be much, much larger. It can be 1,000 to like 100,000 miles across. So imagine something, that core, the size of the nucleus is only like the size of a neighborhood, and all of a sudden you have a cloud of gas that surrounds it that's like the size of the Earth, or many times the size of the Earth. And in fact, for comet ZTF, the diameter of that coma was measured to be something on the order of 100,000 miles across, like 10 times the diameter of the Earth. Just enormous. And that's what we see when we look up in the sky. We aren't seeing that little nucleus, that little ice nugget in the sky. We're seeing this enormous cloud of gas that's surrounding it, that's caused by that ice nugget starting to evaporate its material into this cloud. And then finally, the really characteristic thing that tells us that it's a comet is the tail that drags out away from the sun. And that can be even larger. That can be hundreds of millions of miles in length, equivalent to the distance between the Earth and the sun. So all of this caused by this little tiny ice nugget that's like a mile across is pretty wild. Tails come in two kind of types, and you may see this. You can certainly see this with Comet ZTF. There's what's known as the dust tail and the ion tail. These are caused by different features within the comet itself. Essentially, as the comet gets into the inner solar system, it's being heated up by light that's coming from the sun, and that light causes the ices to melt, but it also and turn into gases, and it releases dust, which kind of drags out behind the comet. But at the same time, that light hits those gas molecules and it knocks off an electron, and it ionizes. It causes those gases to be ionized, which means they have some sort of magnetic charge or electrical charge, and they respond to magnetic fields. And what's important about that is, usually when we think of the sun, we just think of the sun as shining, but it's also, it has something called the solar wind. There's material coming off the surface of the sun constantly. This is a video taken with the NASA SOHO satellite staring at the sun, which is blocked out in the center, and you can see this material flowing off the surface of the sun. Now, that solar wind is charged particles, and it drags with it a magnetic field. And so when it comes past the comet, it drags those ions, those charged gas particles, directly outward from its position away from the sun. And so you get this very distinctive two component tail. One that's the ions. The ion tail tends to be blue because of carbon monoxide, charged carbon monoxide particles that are present in those ions. That fluoresce at that color of blue, whereas the dust tends to be more like what you'd think with dust reflecting off sunlight, which is this kind of murky white color. And this is just another kind of cartoon demonstrating this effect. As the comet travels along its orbit, you get the ion tail dragging directly away from the sun, and the dust tail kind of being a combination of away from the sun as well as away from the direction that the comet is traveling, because it carries some inertia with it. This is another kind of diagram showing how you get two different tail components from comets as they travel in their orbit. Okay, and this is Comet ZTF. This is footage that was taken from several frames by a very good amateur astronomer, showing the evolution of this dust tail as it travels away from the sun and away from the comet. I'm sorry, the ion tail as it travels away from the comet. Pretty spectacular. So this comet, Comet ZTF, has been dubbed by the media the Green Comet, and appropriately so. You can see it has this very distinctive green color. That green color, a lot of people are asking, is due to two certain types of molecules that are present in the comet that are released when the sunlight hits the ices and starts to release the various different molecules. These are diatomic carbon, which is just two carbon atoms that are bound together very strongly, and cyanide or cyanogen, that is carbon and nitrogen that are bound together. And when they get hit with additional UV rays from the sun, it bumps them up, it bumps their electron up an energy state, which then drops back down, and when it does so, it releases this very characteristic green color that we associate with this comet. But what's odd is there are lots of green comets. This is not a unique green comet. You can see these are just four kind of randomly selected comets from the last 10 years or so. And they all have that characteristic green color because they all contain this diatomic carbon and cyanide that are present in the comet itself, and it shows up in the coma associated with these. So really calling this the Green Comet is a little bit of a misnomer. It's like pointing to a person across the street in a crowd and being like, oh, look at that guy, that brown-haired guy, as if brown-haired guy would be some sort of unique identifier. It's not. There are many brown-haired men, and there are many green comets. So yes, it is a green comet, but is it special and unique because of that? No, it's not. And in fact, going further, the media is really playing this up as being this unique comet. It's not really. There are lots of comets that become visible to the naked eye. About once every 2 or 3 years, there will be a comet that comes into the inner solar system, and we can see it without the aid of a telescope like this. And And that's cool, and that's a visual spectacle, and it's great to get us all talking about science and in astronomy. And because I have a love of comets, I'm excited to talk about them. But there's nothing really particularly unique about this comet as it comes in and has its apparition in the last few weeks. So why do comets look this way? They interact with the sun to produce this cloud and a tail that becomes very bright and visible to us here on Earth. Okay, I just want to throw this in there because I think it's super interesting. What about meteor showers? Everybody's familiar with a meteor shower. It's when you see shooting stars across the sky on a particular night or nights of the year. The most popular ones are like the Perseids or the Geminids or the Leonids that happen in the latter part of the year. And they're basically caused by comets. Remember, comets are traveling in their orbit. They're releasing gases and such and dust from their interior, and that fills their orbits behind them, the dust particles. These can be as small as sand grains or pebbles or sometimes larger boulders, but that basically sits in their orbit as they go repeatedly around the sun. Now, if the Earth ever happens to pass through that orbit, it's going to run into all of those sand grains, and those sand grains are going to travel through our atmosphere and burn up in our atmosphere, causing a bunch of shooting stars to occur all within, a night or 2 nights or 3 nights or something like that. So really, meteor showers are caused by comets like Comet ZTF. We aren't traveling through the orbit of Comet ZTF. We are traveling through the orbits of other comets like Halley's Comet, and that's why we get these sorts of meteor showers. But it's all related. It's pretty cool. So meteor showers are just debris from comets entering our Earth's atmosphere. Okay, so how was Comet ZTF discovered? It was discovered just a year ago by CalTech scientists at the Palomar Observatory. This was the largest telescope in the world for about 50 years. It's in Southern California. It's kind of northeast of San Diego, a couple hours drive, hour and a half drive or so. And this is it's a beautiful, beautiful site. And it continues, even though it's no longer the largest telescope in the world, the site continues to host world-class science that's being done. And one such project is called the Zwicky Transient Facility. And what that means is, what that's doing, it's known as ZTF. What it's doing is it's scanning across the sky and making images of the night sky every couple of nights. It'll take a picture over here, and then a picture over here, and then a picture over here. And it does that repeatedly until it covers the whole night sky, at least as visible from the northern hemisphere. And it does it again 2 nights later. And the point is that if you take a picture of some part of sky tonight, and then you do it again 2 nights from now, and then 2 nights after that, and you look at consecutive images, and you look for differences between those images, you can see changes in the night sky. You can see when a star explodes as a supernova. It might not show up in the first image, but it might show up brighter in the second or third images because that was the time scale over which it got brighter. It also picks up things like asteroids or comets that are moving relative to the background stars. And that's precisely how Comet ZTF was discovered. Each image of these 5 images was taken 3.5 minutes after the preceding one. And you can see some of the objects here, these are just stars in the corner, they're roughly the same brightness and same position from exposure to exposure, whereas this object is moving over the course of the 5 exposures. And so we know it's in the solar system and moving relative to those background stars. So this was done March 2nd, 2022. And the team that was credited with the discovery formally goes to Frank Maskey and Bryce Boland. Frank Maskey wrote some of the software for being able to figure out what objects were moving. I also include here Dmitry Duev, who did a bunch of the machine learning software for being able to identify the changing orbits and the changing position of these various different objects that aren't just stars in the background. And then Bryce Boland was actually the person who identified and looked at the frames and was like, oh, this is a real object. These are all CalTech scientists. And initially it was thought that this was just an asteroid, but as they continued to watch this and people from the community continued to watch this, you started to see a tail develop behind it. So this is kind of a time lapse showing from June 2022 until December 2022, as this object got closer and closer to the sun, this is the distance to the sun, 3.5 astronomical units, and then closer and closer until it got about the same distance as the Earth is to the sun, it gets, as you can see, it develops quite a tail and it gets brighter and brighter and brighter. So why does it, this is the official name of the Green Comet, or Comet ZTF, and why does it have this kind of crazy name? Well, it's basically, lots of comets are discovered, you know, a few thousand comets have been discovered to date, and we have to keep a way of keeping track of all of them in some sort of unique way. So this, basically, all the different parts here mean a different thing. C just means that it's a long period comet, that it has an orbit that takes it longer than 200 years to make an orbit around the sun. In this case, it's about 50,000 years to make an orbit around the sun. This part just means the year and month of discovery. So it was discovered in early March of 2022. The E basically means A is the first half of January, B is the second half of January, C is the first half of February, and so on and so forth. So this is the first half of March. And 3 means it was the third object discovered in that period that was a comet. And finally, ZTF just refers to the team that discovered it. Instead of saying the specific members of the team, it just gives credit to the whole team as a whole. Okay, so how was it discovered? Comet ZTF was discovered by CalTech scientists at using the Palomar telescope as part of the Zwicky transient facility in March of 2022. Where is it going? This is a picture showing its orbit in the solar system, and you can see that, you know, a year ago it was out around almost to Jupiter's orbit, and it's slowly come in almost perpendicular to the plane of the solar system. And right now it's basically at its closest approach to the Earth and to the sun, so it's going to be brightest in the sky. But, you know, the media is kind of saying like, oh, you have to see it right now or else it's gone forever. Well, that's not true. I mean, it's not vanishing. It's just traveling into the outer solar system, and it'll get progressively fainter over time. But you can still see it if you look up in the night sky. Because it's moving through the solar system, its position appears to change every night relative to the background stars. This is just giving us an idea of where it was in January and then now into February. Right now it's in the constellation of Auriga, if you're looking. And finally, this shows its brightness over time. And so a year ago, it was very, very faint. You had to have a very powerful telescope and know exactly where to look, where to see it. Whereas on February 1st, at its closest approach to the Earth, you could see it quite readily from a dark sky site. It was above the naked eye limit, so you could see it unaided if you knew where to look. You didn't need a telescope or binoculars. Although here in Los Angeles and Pasadena, we have a lot of light pollution, so it wasn't necessarily possible. But I was able to use a telescope in front of my sidewalk on my apartment building in a pretty, as you can see, light polluted place, and I was able to take this humble image of the comet. You don't see the green color, but you can definitely see the halo, or rather the coma of the gas cloud that's kind of surrounding it. And yeah, this is kind of representative of what you might be able to see with okay optics, a reasonably decent telescope or binoculars or something from an okay site. So where is Comet ZTF going? It's traveling back to the outer solar system. It's fading in brightness slowly. And honestly, it has this 50,000 year period. We believe that it came into the inner solar system about 50,000 years ago based on its current orbit, and it's made multiple passes in the past. But due to its outward trajectory, it's on the edge of whether or not it's actually going to return into our solar system. It might continue beyond and become unbound, gravitationally unbound. It has an eccentricity of just around 1, which is when something is no longer bound to the solar system. So we don't really know. But either way, we probably won't live to see its next passage if it does have one. So in summary, comets are these dirty snowballs that form in the outer solar system, and they start to develop this comet-like shape that we associate with them when they come into the inner solar system and start getting heated up with interactions with the sun, both from the solar wind as well as from light. Comet ZTF was discovered by CalTech scientists as part of this ZTF survey about a year ago. and it made its closest approach just last week on February 1st before heading back out into the outer solar system or potentially beyond. And then, honestly, Comet ZTF isn't particularly special. There are lots of green comets. There are lots of bright naked eye comets. But it is cool that everyone's excited about comets and science right now. So I figured I'd give some sort of context. Don't despair. There are 2 more comets that will be visible. Well, one just next year, Comet 12. Keep an eye out for Comet 12P Pons-Brooks that will probably be as bright or brighter than Comet ZTF in about a year's time. And hopefully we'll all live long enough to see the next apparition of Halley's Comet that's supposed to come through here in 2061. It has a period of about 75 years. It was last year in around 1986, and has been coming here for centuries. So that's always a great comet to see.
That's the end of the first talk. So if you wish a cup of tea or coffee, feel free to get up and go. I'll start the second talk in a moment, which will go for about 20 minutes as well, about simulating the universe on a computer.
I'm talking to my specialist about this 20 years ago.
Yeah.
Simulating the universe on a supercomputer. Very matrixy here. Quick outline of the talk. Can you guys see it okay? I'm going to drop the lights a little bit. Okay, that's a little bit better. So very quickly, why do we use simulations in physics in general, but specifically in astrophysics? How do we actually simulate physical systems? What do we simulate, and on what sort of computers are we doing these simulations? So first off, why do we use simulations in astrophysics? Well, what's the whole point of science? Can I get a really, this isn't a rhetorical, what's a quick response to, why do we do science? Why is science out there?
Understanding the universe.
Understanding the universe. Very good. Very, very succinct. Yes. We do science to better understand the nature of nature. How nature evolves, how nature creates a variety of things. So here's this beautiful scene of the natural world. And scientists might ask, why are there mountains? Why is there snow? Why is it colder on the tops of mountains as opposed to down in valleys? Why do trees grow? Why do clouds form? What are clouds made of? All of these things are questions that can be addressed by science. And how do we address them? I won't ask that because I'll get lots of shouts back. But with the scientific method. And I'm sure everybody remembers back in their science class of doing the scientific method, where you form a hypothesis, you set up an experiment with initial conditions, you run that experiment, get some sort of results, and then analyze those results to conclude whether or not your initial hypothesis, your initial guess of understanding that something is correct, and if it's not, how you can change that, how you can modify it to make it better, and then redo this over and over and over again until you finally, at the end, hopefully understand something about whatever system you were experimenting on. In terms of astrophysics, most of what we know about the cosmos we get from light that's traveled from those objects to us. And we can't, per se, set up experiments in the same way that other natural sciences can. We can't set up a galaxy like the Andromeda galaxy here and a star over here and just run it forward, because I don't have the power to move galaxies around or stars around. Do you guys? And even if we could, the timescales associated with these things changing and evolving are so long that we'd have to be waiting over the course of a lifetime or longer. For a galaxy like the Andromeda galaxy to evolve any substantial amount takes millions or sometimes billions of years. So it's just not realistic for us to do these sorts of experiments on astrophysical phenomena. But it is inside of a computer. In a computer, you can make a virtual experiment. You can make a virtual space and set up your initial conditions in whatever way you desire, as long as you program in appropriate physical laws, and then you can run it forward, and you can accelerate time to see how it might evolve and produce whatever it is that you're trying to study. So, to run virtual experiments, that's one of the reasons why we use simulations in astrophysics. Furthermore, when we run these simulations, if I'm doing a simulation of how these galaxies are evolving, or how to form something like this galaxy, and I'm actually able to do that, it's indicative that I really have a good grasp of what's happening in that system. I mean, I programmed in the physical laws, I programmed in the initial conditions, and then I ran it, and I was able to produce that. That tells me that I hopefully really understand what's going on in that system, because I created that system. So it helps us not just to run these experiments but to better understand the natural world. And finally, if we take these astrophysical systems and we're evolving them forward in time and running them forward in time, we can run them forward past the present time into the future. And that's actually super cool, because it means we can predict the future, which is like magic. If you can predict the future, it's pretty spectacular. So for all these reasons, we run simulations to try and better understand the natural world. OK, so how do we actually simulate physical systems? We'll just give a quick rundown with our handy-dandy computer here. We write a program creating some sort of virtual space inside of our computer. And we'll get more into that in a moment. We program in, just like any experiment, we program in our initial conditions. We program in whatever dominant physical laws we think should be acting in our particular simulation. And you might think, let's program in all the physical laws. But unfortunately, with the computational power that we have, even the best supercomputers that we have, if you program in all the physical laws and have infinite spatial resolution in your models, you won't make any progress at all. We just don't have the computing power to do it. So if you came thinking that I was going to be talking about how the matrix, we're all living inside a computer program, unfortunately, we don't have the computational power or the algorithms yet capable of modeling things as complex as that, especially the complexity of free will and how people interact with each other, which is beyond what I study. And then we run it forward in time, and hopefully out comes science. So this is pretty vague, but how do we actually simulate physical systems? So I'm going to give an example that most of you, in fact all of you, should be relatively familiar with, if not in necessarily these kind of formalistic terms, but that is the equations of motion, which is essentially how do objects move? We interact with moving objects every day. So stay patient through this. The equation stuff will be relatively short, but I just wanted to give some formal background. So at time t, any object, and we'll use this bouncy ball, which lights up to make it even more spectacular. Any object possesses a position in space, a velocity, which is just a fancy word for speed, but with a direction, and an acceleration that I'm representing here as x, v, and a. So any object is going to have a position, and we'll just represent position in the x direction here. So this is position 0, 1 foot, 2 foot, 3 feet, and so on and so forth. And when we give something a velocity, or when we give it a speed, we're essentially telling it how that position is going to change with time. And when we give it an acceleration, we're telling how velocity changes with time. OK, so the key point to simulating physical systems is to break up time, at least in this case, breaking up time, and usually in simulations, break up time into discrete steps, to break it into individual steps. That is to say, take something that's in motion, start at your initial conditions, move it forward in time just a little bit, like a second or a half of a second, and see how far it's moved and what its acceleration has done and what its position has changed, and then reevaluate those equations at that new point in time and see what its new velocity should be and its new acceleration and its new position. And do that forward. And essentially what you're doing is approximating how things move by breaking them into these discrete steps. And yeah, this is basically what I just said. At each new time, we can calculate the new position or velocity based on using the previous position, velocity, and acceleration. So a concrete example, a stationary ball. This stationary ball, we'll set it on the table here. I'm going to hold on to it because who knows what's going to happen when I release it. We give it a position of x equals 0, which is to say it's just sitting here at this position. We give it a velocity of 0. That is to say I'm not going to hit it and cause it to give it any speed whatsoever. And it has an acceleration of 0, which is formally true. It is being accelerated towards the surface, towards the center of the Earth, but the table is counteracting, so it doesn't have any net acceleration on it at this moment. So what do you guys think is going to happen if I release this ball?
It'll stay there.
It'll stay there. I gave it away with stationary ball. So we release it, and for the most part, it stays there. There's a little tilt to the table. But what we can do is at time equals 0, we give it our initial conditions. At time equals 1, we evaluate. We multiply the velocity of it times that time step that we have. 1 second, we'll call our time step 1 second. But it doesn't have any velocity, so it doesn't move. It doesn't change its position. And it doesn't have any acceleration, so it doesn't change its velocity. So that's a really boring example. Let's do something that's a little bit more interesting. A rolling ball. Same initial conditions, same position, same acceleration, but now we give it an initial velocity. We give it an initial velocity of 1 foot per second. So I'm going to hit this so it's traveling and it's covering 1 foot per second. And then we'll say that the time step associated with it is 1 second. So how far should it travel? This is not a trick question. How far should it travel in 1 second? 1 foot, exactly. So I'll see if I can do 1 foot per second. That's roughly 1 foot per second. And if we were simulating this, as we do here, this is the ball, this is the x-axis of the table, and this is the time. So we run it forward in time steps, and at each 1 second interval, we reevaluate its position and its velocity. Again, it's a pretty boring example, but I wanted to start simple before we get into more interesting things. We can also shrink that time step, and it actually gives us better behavior. It's more computations to make, but it should give a better result. So if we do this, all I'm going to do is change it so the time step, instead of being 1 full second, is 1/100th of a second. So in 1/100th of a second, a ball traveling at 1 foot per second, how far should it go after 1/100th of a second? 1/100th of a foot. And then we reevaluate how far it, or what its new position, velocity, and acceleration is after 1/100th of a second, and then after 2/100ths of a second, and so on and so forth. And we get more smooth behavior of the ball as it travels across the table. OK, so this is all pretty boring, and you're like, why did I drive 30 minutes to come see this? Here's potentially a more interesting example, a bouncing ball. Now, I've represented 2 balls here in my simulation. One that has the black arrow that's traveling to the right has an initial side velocity to it. So you'll see it demonstrates the motion a little bit better. And blue represents the acceleration, because now our ball is being accelerated to the ground. I'm going to drop it from 2.5 meters. That's why this is at 2.5 meters, which I calibrated to be the height that I can reach when I reach to the top here. And we're going to drop it and see what happens. And of course, you guys have all played with these things before. You probably know what's going to happen, but we can make calculations about this. Now we have an acceleration. We have a position in the y direction as opposed to the x direction, y just being the vertical axis, which we can treat the same way. And let's make a prediction. We'll run it forward, and you can see the black arrow representing the velocity vector is preceding that ball. Now, I've added in an extra piece of physics, and that is when the ball reaches the ground, it strikes the ground, and it translates its downward velocity into upward velocity. Or else this would be a really boring simulation. It would fall, and it would stop. So we have this prediction. So let's see how accurately this prediction holds up. So if I hold it up here, and I'm not watching, so you guys will have to... Is it bouncing at the same rate? Oh, now it lost a little bit there. But for the most part, we can predict how this thing is going to behave with time simply by taking discrete individual time steps and calculating what the new position, the new velocity, and in this case, it's the same acceleration that's acting each time, but seeing how that changes over time.
Future predicted. We predicted the future. It's not a very interesting future, but we did predict the future. So let's get on to something more interesting. Let's talk about astrophysical systems. And this will be the last equation of the talk, so fear not. Gravity. Everyone's familiar with gravity. Gravity is what's holding us to the surface of the Earth. But in astrophysical systems, gravity basically is a force that attracts anything that has mass to anything else that has mass. If there are two objects, me and this ball, for instance, we each possess matter, we each possess mass. We're pulling towards each other. I'm pulling towards it, and it's pulling towards me. It's not very much, because as you can see, the acceleration that we're being pulled by gravity is proportional to the mass of the other object. So, for instance, this isn't very massive, so it's not pulling me towards it very much, or it's not pulling you towards it. But the Earth is very massive, and that's why we're being pulled towards the Earth so dramatically. But in our own small way, we're pulling the Earth back towards us. Not very much, but we're doing it nonetheless. And you may also see that there's an x squared here. Remember, x is our position, so the acceleration is proportional, it's inversely proportional to the distance separating the two objects, which is to say the closer two objects are together, the more they're accelerated to each other. So even though the sun is 1,000,000 times more massive than the Earth, so it should have an enormous acceleration on us, it's much, much, much farther away than the Earth is to us. And so it's not pulling on us quite so much as the Earth, which is very close, even though it's not as massive. OK, so what does this mean? It means if we take two stars that are represented here as red dots, there's a mutual acceleration from both of them on each other. And the closer they are, the blue arrow represents the acceleration. The closer they are, the more they're accelerating each other towards each other, if that's an English sentence. But let's see a demonstration of this. So here's an example. We've got the sun in the middle. This is not to scale. The sun in the middle and the Earth over here. The distance separating them is called an astronomical unit, which is the distance between the Earth and the sun, but it's several million miles. I'll give them no initial velocity, and the acceleration is just calculated by gravity. And remember, gravity is an attractive force, so this is being pulled that way, and the Earth is being pulled towards the sun. So let's see, what do you guys think is going to happen? Boom. Boom. Good. OK. So we run it forward, and boom! The Earth runs into the sun. Don't worry. This isn't how things are. But if you'll see, I'll just slow this down for a bit. If you'll see, initially what happens is, well, the blue arrow represents the acceleration. The Earth is being accelerated more towards the sun than the sun is being accelerated towards the Earth because the sun is more massive. And that acceleration is causing that black arrow, the velocity vector, to grow with time. As they get closer, the blue arrow gets more, because remember, the closer things are, the more acceleration there is between them. And finally, they just run into each other. OK. Don't worry, though. The Earth actually does have some velocity that is traveling transverse to the direction of the sun. So this is the exact same simulation, but it's done where we give the Earth a little bit of velocity. And so it starts to travel in an orbit around the sun. And again, we're doing at each discrete time step, we're calculating the equations of motion. We're calculating what the position, the velocity, and the acceleration are. We're just using our acceleration to be calculated by gravity. And you notice that always the blue arrow from the Earth, the acceleration of the Earth is towards the sun, and always the acceleration of the sun towards the Earth the acceleration of the sun is towards the Earth. But the velocity is not in that same direction. The speed is not in that same direction, which means that in the time that it takes the Earth to move one time step here, that velocity vector is pulled closer to the sun, but it's traveled in distance, so it's always perpendicular. So it remains in this nice little orbit. OK, so that, again, isn't that interesting. But this is kind of interesting. So I wrote this code that we're looking at these silly little simulations in Python yesterday, just to demonstrate this stuff. And on my laptop, I was able to calculate the trajectory of the Juno probe that happened on Monday. Did you guys follow this? Juno was this this probe that NASA sent into space 5 years ago, and eventually it made it to Jupiter, and it made it to Jupiter on the 4th of July, just on Monday. So here is the Sun, here is the Earth and Juno, and here is Jupiter. Again, not to scale, because my simulation code is not fancy. And here's Juno traveling outward in its orbit. Earth is going in its orbit. Each orbit is 1 year, because that's how the Earth works. And Juno sneaks in there and gets a gravitational assist out into the outer solar system on its way to hitting Jupiter. And it takes a while, because they're moving pretty slowly, and that's a long distance. And boom, Juno enters Jupiter's orbit. That's pretty cool. I mean, I don't have a $1 million budget to do all these things with the supercomputer. Well, I mean, I can use a supercomputer, but I did this on my laptop. So we're able to predict the future about how Juno got all the way out to Jupiter. 1 second. So how do we actually simulate physical systems? By approximating solutions to certain physical equations and discretizing time. So breaking time into individual chunks and reevaluating the nature of the system at each of those chunks as we move forward. It's not always time, but oftentimes it is. So what sort of things do we simulate? Along the lines of what I was just demonstrating with that simple simulation code that I wrote, there was work done in the 1970s, kind of the pioneering work by Toomre and Toomre, that did this for trying to showcase how you get certain structures, which aren't showing up very well here. I'm going to darken it just a hair. Don't worry, I'll turn the lights back on in a moment. So you can see when galaxies are interacting with each other, you get these bridges and tails that come off them. And no one really understood why this was the case until they did simulations much like the ones that I just showed, where you have two galaxies that are represented as a number of individual points of mass, like my ball here, and then allow them to interact gravitationally with the equations of motion. And so this is like a time series. So it starts out like this, and it goes forward in time. And eventually, you're able to form these bridges that connect the two. And it's just the effects of gravity on massive objects that are rotating like these galaxies are. Actually, I'll leave the lights off for a moment. We can incorporate hydrodynamics into our simulation. Hydrodynamics are just they're the physical theory for how gases interact with each other and behave. They're quite a bit more complicated than the equations governing gravitation. However, they can still be broken down and discretized into these approximations and approximate solutions in the same way that we did for those very simple equations, the equations with gravity. And so kind of a combination of those, this is a nice video of the merger between our own Milky Way galaxy and the Andromeda galaxy, our nearest massive neighbor. And you can see here is a time scale from the future of these two objects interacting. So here's the Milky Way, here's Andromeda, this is the Triangulum galaxy. And they are on a crash course. They are moving towards each other and will merge at some point in the future. It's like 6 billion years off, so we don't really have to worry, but it is going to happen. And so this simulation incorporates gravity and hydrodynamics, done by some colleagues of mine. And you can see what happens when they merge. You get these, again, those tidal tails, those bridges and tails that come off the systems. But then they eventually coalesce into a single galaxy, which people tend to call Milkomeda, because it's Milky Way and Andromeda merged together. So you see this galaxy that results is quite a bit different looking than either of the progenitors. And it tends to be redder because it's more made of older stars. Young stars tend to be blue, but during that merger, you blow out a lot of the fuel for star formation, so there aren't a lot of young stars being made afterwards, and you just have a stellar population that's made of old stars, so it tends to be redder. But again, this is 8 billion years in the future, so don't sell your stock yet. Furthermore, they were able to put together images of what the night sky would look like. So here's the Milky Way that people are potentially familiar with, and here's Andromeda getting bigger in the sky until it's enormous. And then there's the merger going on, and then when you look up in the night sky, you just see this kind of haze of reddish stars in the galaxy Milkomeda But this, again, this is 8 billion years in the future, so don't worry about it. But the point is, future predicted. Future predicted. OK, what else do we simulate? So more galaxy evolution. I'm biased because I work on galaxy simulations. This is work done by one of our colleagues here, that a number of people are graduate students that are working with him. I work with him. His name's Phil Hopkins. He's a professor here. And this is a zoom in on a simulation of an individual galaxy that consists of gas and gravity and a number of other effects. And so we can get a somewhat realistic looking galaxy system that we've totally simulated and created on a computer. But it looks a lot like what you'd see when you look at Hubble Space Telescope images of galaxies in the sky. What's more, we can simulate how supernovae occur. This is a simulation done, a hydrodynamic simulation done, of the moment at which a supernova, a type 1a supernova, explodes. And you can see this is the stellar surface, and this is the interior where it's starting to cause this enormous hot jet that's exploding out the side of a supernova. So for those of you who don't know, supernovae are what occur in a variety of circumstances, but typically when stars, massive stars, run out of material to hold up their interiors, so they collapse under their own gravity, and then they explode in an enormous explosion. And that's essentially what's being modeled here and visualized here. Pretty spectacular stuff. And then finally, we can model a representative volume of the entire universe. We can't represent the entire universe, but we can take a representative chunk of it. In this case, this is one of my simulations. It's 100 megaparsecs on a side, so it's 300 million light years across one of these dimensions. So it's quite a large volume of space. And as you can see, because it's all white in here, and everything is basically the same color, it means that in the early universe, and this is only a few million years after the birth of the universe, the density of material is pretty uniform. There's not that much difference between this spot and this spot in terms of the mass content. It's all a very uniform, hot volume. But there are slight overdensities which are enhanced by gravity. Remember, we were talking about gravity as an attractive force. So if something has a little bit of an overdensity, it has a little bit more mass, it's going to attract this area that has a little bit more mass. And they'll coalesce into a more massive thing. And it turns into a runaway effect. And that's what we see here when we evolve it forward. You see brighter areas tend to be higher density areas, and darker areas are lower density areas. So what happens is you get this runaway effect where massive areas get more massive. And so they attract more stuff to them, and they get more massive. And you find filaments of material, of higher density material. And where those filaments coalesce, you find knots of material. And those knots are where galaxies form and clusters of galaxies form, because that's where the overdensity of material is. And in between those filaments and in between those walls of matter are these voids that are devoid of a lot of stuff, including galaxies and stars and that sort of thing. And we run these simulations, and they reproduce the overall distribution of matter that we see when we look up in the sky. When you see the sky, when you catalog where galaxies are located, they are not located just uniformly across the sky. You'll find them in filaments and walls, like we can reproduce in simulations. OK, so what do we simulate? All astrophysical systems that we can get our hands on: planets, stars, galaxies, and the universe. And finally, on what computers do we run our simulations? Well, as I was saying before, the simulations that I did simplistically for this talk were just done on my laptop. I mean, you can do decent simulations on your own laptop and still make progress. But for the most part, we want to run the highest level simulations that we can on the highest power computers that we can, which is to say on supercomputers. So, have you guys all seen The Martian? There is a... Oh, what the heck is this? I was watching it before. Let's hope it works. Oh no. Thwarted. Okay, well, there's a scene in The Martian. I'll just describe it to you. There's a scene where a character, and I don't think I'm ruining too much about the film with this, a character goes to a supercomputer and he plugs his computer directly into the supercomputer and then does his calculations, and then at the end it says, calculations correct. This does not happen. And you don't need to go to a supercomputer in order to use it. Just like any computational resource in this day and age, you can connect to it over the internet. You can do your stuff over the internet. The computer that they use in that movie is a real NASA computer. It's called Pleiades. This is a very similar machine that I use. It's funded by the National Science Foundation. It's called Blue Waters. It exists in Urbana-Champaign, Illinois. This is the building that houses it. It is such an expensive piece of infrastructure that they have built it to withstand a plane crashing into that building and bombs exploding. It is a very secure site because it's worth a lot of money. And it's a lot of our infrastructure in computational science, not just astrophysics, but all computational sciences. It consists of rows of these towers that just house computers that are running all the time. In this particular system, there are 360,000 processors that you can access and run your computer code on. And as you might guess, they don't give access to everyone. You have to apply for time because it's extremely expensive. You apply for time, and then they might give you some amount of time on this machine to be able to run whatever code that you think that you can run to answer a particular science question. And because I promised to do some work on a supercomputer, hopefully I'm not thwarted on this front as well. Okay, so in much the same way that you connect to anything on the internet, you connect, in this particular case, I'm connecting via SSH, which is a secure manner of connecting. You have to use this little RSA key, which is like on your phone where it does the authenticator and make sure two-point authentication is working. So I SSH into Blue Waters. I have to enter my password along with the number that's on this thing. Live demos are always a mistake. Oh, yeah, they are always a mistake. I'm just going to turn on the light so I can read this thing. Okay, I'm almost done here. Hopefully my password will be accepted. Hooray! Okay, so, and basically what you do when you log in is you have your computer, you install your software that you might need. Generally, software that we use is all written by scientists in general, so I'm one of the authors of the software that I run. You submit a job to the computer to run on its own time through a queue. In this case, I'm asking for 24 hours on 512 processors, and I do that. Queue sub, submit, oh, job submitted. And then you wait like 3 days for it to go through the queue, and it runs your code, and then you try and analyze it. So it's not very interesting, and certainly it doesn't end when you're finished. It doesn't give you calculations correct, as it does in The Martian, but this is basically the nature of the game. So, on what computers do we run our simulations? Taxpayer-supported supercomputers run by NASA, or the National Science Foundation, or the Department of Energy. And in general, conclusions of this talk: why do we use simulations? To run virtual experiments on our computer. How do we actually do it? By approximating solutions to physical equations and discretizing some variable, in this case time. What do we simulate? Basically all astrophysical systems that we can get our hands on. And on what computers do we run our simulations? Taxpayer-supported supercomputers. So thank you, taxpayers. Please continue to support science funding agencies. Thank you very much for coming.
Right, we move on to the last talk, which goes for about 15 minutes, showing how Artemis was actually made and taking you into the factory before we close with a visit to the NASA Johnson Space Centre.
Incidentally, the Martian is on TV this week.
Is it? Ah.
I'm not sure if Dawn will come, but a couple of nights this week.
See if the calculations are correct.
It's so impressive to be here, and I really cannot give you a sense of just how massive this thing is.
You see pictures, you see scale drawings, but until you see it assembled and it's sitting on the factory floor, it's like, wow, that's a big rocket.
The average person has no idea how awesome this place is. The things we do here are remarkable.
This is Artemis, NASA's new mega rocket that will take humans back to the moon for the first time in 50 years and take us further into space than we've ever been. For this journey, NASA needs its most powerful and advanced spacecraft ever, a super heavy lift rocket known as the Space Launch System, and an advanced crew vehicle called Orion. Together, they'll lift huge payloads and take humans on long-term missions into deep space. This spacecraft will travel 1,000 times farther than the International Space Station on its very first flight. It's the foundation for building a base on the moon, and one day, it's set to launch to Mars. It's an epic build on a massive scale, and it's being built here at America's Rocket Factory. A short drive from the centre of New Orleans on the edge of the Gulf Coast is the Michoud Assembly Facility. Since 1961, this building has been a cornerstone of NASA manufacturing, and it's the heart of the Artemis build. For the past 60 years, NASA has been building the future of space exploration. First to the moon with the Apollo program, and then with 135 shuttle missions. You can see those shuttle mission patches behind me. Now they're doing it all again with the Artemis program, going back to the moon and further into deep space than ever before.
Everything we've built for NASA has been a crewed vehicle. Starting with the Saturn program, obviously put men on the moon. The shuttle program, we built the external tanks here, which obviously put humans in orbit. And the shuttle program built the International Space Station. And then today, Artemis will put humans back on the moon and on to Mars.
Right now, NASA is focused on the first 3 Artemis flights. Artemis 1 is set to launch in 2022. This first flight will orbit around the moon without astronauts. It's a sort of test flight designed to collect data on the capabilities of the Space Launch System, the Orion spacecraft, and all the exploration ground systems that support flight. On Artemis 2, NASA will send crew up for the first time for a flyby of the far side of the moon. It's the first time humans will have been that far into space since the Apollo program ended. That flight is set to launch no earlier than 2024. By Artemis 3, a third rocket will take humanity back for a moon landing, no sooner than 2025, sending the first woman and the first person of colour to touch down on the moon's south pole and press their footprints into the lunar surface. At Michoud, NASA contractor Boeing is making the core stage of the Space Launch System, or SLS. It's also where Lockheed Martin is building the Orion pressure vessel, the main structure that holds the pressurized atmosphere for the astronauts to survive in space. A build of this scale takes up a lot of room. Getting around this building, it's quicker to ride a bike than to actually walk.
And what you need is large open spaces. I mean, the rocket, the core stage is 212 feet long. So you got to have wide open aisles, you got to have spaces with cranes to be able to lift a heavy rocket. The floor loading, which people don't realize in South Louisiana, there's no bedrock. So the floor in here has to reinforce to support the weight of the rocket.
So what we're looking at right here is a scale model of the Michoud assembly facility. It might not look very big, but this is equivalent to 2 million square feet of factory space. That's 31 football fields, all dedicated to building rockets. It's kind of impressive to see it from this level. I feel kind of powerful. To understand the Artemis build, it's worth doing a little bit of Rocket 101. The bulk of Artemis is made up of the massive SLS core stage. That contains the liquid hydrogen and liquid oxygen tanks. They power the 4 RS-25 engines on the bottom of the rocket. On either side of the core stage are the solid rocket boosters. These are actually heritage parts from the shuttle program, though they've been upgraded with new avionics and capacity. They'll provide about 75% of the lift for the rocket. The SLS launches the rocket into space, but it's jettisoned early in the flight. That's when the rest of the spacecraft, what you can see in white, takes over. That starts with the Interim Cryogenic Propulsion Stage, or ICPS, which guides the spacecraft on its path to the Moon after launch. Above that is the Orion crew vehicle, which carries the crew and support systems. Then at the very top is the Launch Abort system, which is there to propel the astronauts to safety if something goes wrong during the launch. The whole of Artemis 1 is 322 feet tall, taller than the Statue of Liberty. And while it's a touch shorter than the Saturn V from the Apollo era, it can lift 1.3 million pounds more payload into space. The rocket designed for the first 3 Artemis missions is known as Block 1, and it can be configured for crew or cargo. But NASA is already looking towards the future. The next generation rocket will have a much more powerful exploration upper stage with 4 engines and 4 times the thrust. That next gen rocket will help NASA send crew and cargo on longer missions to the Moon, Mars, and beyond. Since the early 70s, NASA has only sent humans to low Earth orbit, a couple of 100 miles above Earth. Now, it needs to protect astronauts on longer missions into deeper space. For that, NASA has partnered with Lockheed Martin to build a new kind of spacecraft, Orion. With Orion, the stakes are critical.
When you build a spacecraft, you can't make mistakes. You're going to an environment that no one and nothing ever sees. It's a harsh environment, but that's why they're astronauts and we aren't.
The Orion crew vehicle is made up of a number of sections. At the base is the European Service Module, built by the good folks at the European Space Agency. This will guide Orion through space and around the Moon, long after the SLS is out of the picture. It also contains enough food and water for a 3-week mission. Above the service module is the crew module. That's the pressurized capsule that Lockheed is building. It's a third larger than the Apollo command module, and its computing systems are 4,000 times faster. It has 4 crew seats, a compact exercise machine, and a toilet with its own door. This capsule doesn't just have to keep the astronauts alive in space, it's got to protect them when they come back to Earth too. During re-entry, Orion will travel at almost 25,000 miles an hour, so it's going to get hot.
For the low Earth orbit vehicles, when they return, they got to withstand about 3,000 degrees during re-entry. The Orion capsule has to withstand about 5,000 degrees. And so the heat shield and the thermal protection systems on the aft end of the vehicle are significantly different.
While the Orion build doesn't take up too much space at Michoud, the SLS is a different story. Think of a regular car production line, but way bigger. Because in this case, we are building rockets. And yes, they're actually building them right now. That's all the banging and crashing you can hear. So we take individual panels, they get welded together into larger sections, and then those sections form up the parts of the rocket. All that assembly takes place along these stations, and then the final assembly is way down the other end of the building. The SLS is made up of the massive liquid hydrogen tank at the bottom and the liquid oxygen tank on top. These tanks need to withstand huge pressures. The launch of this rocket is essentially a controlled explosion after all. But they also need to be as light as possible.
So if you imagine a Coke can expanded to the size of a liquid hydrogen tank, your barrel wall thickness is pretty close to the same ratio. And the engineering that's been there to be able to withstand the pressure and the hundreds of thousands of gallons of fuel in there is pretty amazing.
All right, so right now I am 7 stories up in the air, and behind me is the Vertical Assembly Center. Now this is where all those components we saw before, those rings, those cylindrical barrels, they all get fed into this tool and get welded together to become the massive fuel tanks. They get fed into the bottom, they inch up, kind of like an upside down Pez dispenser, and what comes out is a fuel tank that becomes the body of the SLS. After the rocket has wound its way through the Michoud production line, it ends up here, the final assembly area. And this is where we find the core stage of Artemis 2, about to finally come together.
The sheer size of the vehicle that we're building here is astounding. The design and the manufacturing talent that it takes to build a vehicle this size for all the engineering folks out there in the world should shock and awe.
So where to from here? Well, these 2 massive sections are going to get joined together, then they add the engine section at the very end with 4 RS-25 engines. Then this whole core stage gets put on a barge, shipped around the Florida Panhandle to the Kennedy Space Center. The core stage for Artemis 1 has already made that journey. After leaving Michoud, it went for engine testing at the Stennis Space Center across the border in Mississippi. From there, it travelled on a 6-day barge trip up to Florida. Thankfully, I could just jump on a plane. So right now I am 16 floors up in the Vehicle Assembly Building at NASA's Kennedy Space Center, and I am here to see the Artemis rocket that will be going to the moon. It's so impressive to be here, and I really cannot give you a sense of just how massive this thing is. It's so impressive. The Vehicle Assembly Building was originally built for the Saturn V rocket in the Apollo days. Now, it's where Artemis 1 is going through its final checks before launch. But we've still got to get to launch day. And like any true space program, there have been plenty of delays. Artemis has been in the works for more than a decade. It was originally slated to launch in 2016. Now, NASA hopes to launch Artemis 1 this year, after finally wrapping up pre-flight testing. As for boots on the moon, 2025 might be ambitious. In fact, NASA's own Inspector General puts that date at 2026 at the earliest. And then there's the cost. The Inspector General says the Artemis program will cost NASA $93 billion by 2025, and each Artemis flight will cost $4.1 billion. What's more, each SLS rocket will only fly once, and there are no prototypes being launched on shorter test flights like we've seen with SpaceX's Starship. This rocket, this is it.
The vehicle we built here, Core Stage 1 and delivered from Michoud, is the same vehicle that went to Stennis for testing, and that test vehicle was then delivered to Kennedy, and that's going to be the core stage that's going to be part of Artemis 1 launch, which is going to be a man-rated vehicle. So you had your prototype test vehicle and launch vehicle all in one.
But when companies like SpaceX are launching and landing the same rockets to be reused, why build a rocket that can only be used once? According to NASA, building reusable rockets comes at a cost, especially when it comes to launching huge payloads to start building infrastructure in space.
Our mission is to get as much mass to the moon as we can on a single launch. When you have reusability, there's extra weight penalties for that. You got to have the gear to land it, you got to have extra fuel. All that takes away mass that you can put to the moon.
NASA is hoping to get a return on its investment. Eventually, the space agency wants to commercialize Artemis and sell it to anybody that needs heavy launch capability. That'll leave NASA to focus on bigger missions to places like Mars. And that's the long-term goal. NASA wants Artemis to get us into deep space for the long haul, shuttling astronauts to the moon, setting up a lunar base, and going to Mars and beyond. That dream is being built on the back of this rocket. It's a vision for a new generation. Artemis, the sister of Apollo, carrying the hopes of space exploration into a new age. And soon, we'll all get to see that vision launch into the sky, ready to forge the next era of discovery.
We don't build washing machines, we build national treasures. And so it's going to be a feeling kind of like the first shuttle launch or the first Apollo launch. It's indescribable, the amount of pride that we feel, when that occurs.
Sounds that people will hear for Artemis 1 at the Cape, as well as, like I said, the emotions and feelings that the astronauts are going to experience as they're going up on this vehicle. It's going to be nothing short of awesome.
You're making history. You don't realize it now, but at one point when you get to be my age, you realize, man, I was there when we started it.
And now we'll come to the closure time. This is a video that goes a couple of minutes. It was produced by effectively work experience students at NASA's Johnson Space Centre. I've been fortunate enough to visit the Johnson Space Centre 3 times while I was working for Shell, because they were based there at Houston. It's actually quite difficult to get to if you don't actually own a car. Because Houston is one of these very car-centric sort of cities, and they've improved it quite a bit from the last time I was there. The massive Apollo 20, which was the one that was due to go up, was out in the open and starting to rust away the last time I saw it, but they've actually moved it inside, which you'll see on some of this. This is something that was put together and approved by NASA, and you might also want to try the toilet roll thing as well.
NASA Johnson style. Johnson style. Welcome to NASA's Johnson Space Center. We are coming in hot, so don't burn up as we enter. We do science every day that affects your daily life. Throw them up for manned spaceflight. Science everywhere as we engineer the marvels that fly through the air and take us way beyond Earth's level. Science everywhere because we engineer the marvels that fly through the air, flies us through the air. Control the mission out of Johnson. This is ground, and this is space. Tell me, Houston, what's the problem? It's okay, oh it's okay, because there's flight controllers on the job today. NASA Johnson style. Johnson style. NASA Johnson style. Johnson style. NASA Johnson style. Hey, Science Navy. NASA Johnson style. Hey, it's amazing. NASA Johnson style. Orbiting Earth International Space Station, where we work and live in space with a crew from several nations. Got Japanese and Russians and that European charm. Throw 'em up like the Canada arm. Kicking out research. 29K cubic feet revolves around the Earth. Science microgravity revolves around the Earth. Columbus jamming destiny. Kicking out research. Kicking out research. Train the Astro, not to Johnson, to go to space, to go to space, cause the missions of tomorrow start today, they start today, as we engineer the future day by day. NASA Johnson style. Johnson style. NASA Johnson style. Johnson style. NASA Johnson style. Hey, Science Navy. NASA Johnson style. Hey, it's amazing. SLS and PCV, we cannot feel the floor. Cause the lack of gravity, the destinations are an asteroid, Mars, or the moon. We are blasting off, start the countdown soon.
Ignition sequence start. 6, 5, 4, 3, 2, 1.
Science Lady. NASA Johnson style. Hey, it's amazing. NASA Johnson style.
There we are. Now that I've given you an earworm for 3 o'clock in the morning when you wake up and you can't get it out of your head. Thank you very much for coming this month, and we'll see you next month at the March meeting.